So this is the last talk for this session, and our speaker is Theo Douvropoulos, who is going to be speaking about Hurwitz numbers for reflection groups. Okay, so Theo, it's all yours.
Okay, that's great. Thank you, Bruce. So thank you, everybody. I'm very happy to be here, even if it has to be online, as the situation is going for the last few years. I have an exciting project to talk to you about. So usually I like things that are particularly nice in the symmetric group, and they have analogs in reflection groups because I'm a student of Ukrainer, former student. So this is another one of those events, right? So I'm going to talk to you about a version of objects that maybe should be enumerated by an analog of Hurwitz numbers for reflection groups. This is joint work with Alejandro Morales from UMass Amherst as well, and with Joy Lewis from George Washington University. I've been very lucky that they invited me to the project. This is, I think, I'm going to persuade you, a really cool one. So I'm going to spend the first few minutes just giving kind of like an overview of the standard, the usual Hurwitz numbers. So the main combinatorial object that's counted by the Hurwitz numbers is certain factorizations in the symmetric group. So what you're doing is you're factorizing a permutation, but you're only allowing your factors to be transpositions, okay? And then you impose certain conditions on that. What are the conditions? The factorization has to be transitive. Transitive means that the collection of transpositions that you use, it acts transitively on the natural set that the symmetric group acts, right? One way to think about it is that you can model transpositions with edges between their corresponding numbers. And then if the collection of edges that you have is connected, then the group generated by the transpositions is all of a sudden, otherwise it would be something smaller. So I have for you two examples, one of a not transitive factorization of this permutation. Right? You see we have two connected components, and another one that is actually transitive. Okay. So the other thing now that can vary is the number of factors that you use. Right? If you fix the number of factors, that corresponds to the genus in some nice surface, and those are the Hurwitz numbers of that genus. So we're going to be interested today mostly about the case where the number of factors that you have is the smallest possible. Right? So the Hurwitz numbers, for us for now, they count factorizations of some permutation sigma that are minimum length, they're transitive, and the factors are only transpositions. Right? So there is a really cool theorem that goes back to Hurwitz in the end of the 19th century. And it says that the number of those things is very nice. It's a nice product formula. So it depends on the cycle type on the permutation. That's reasonable. And check this out. I would like us to remember a few of the important ingredients. So we have a big factorial at the beginning. And even more, the number n plus c minus 2 turns out to be the minimum number of transpositions that are needed. So this is, in fact, the length of the factorization. Then you have this n to the c minus 3 that should remind you of like counting trees or cacti in a certain sense. And then you have some sort of nice product formula with a lambda i's. The special case of this formula, if you count factorizations of the long cycle, you get n to the n minus 2, which is the number of trees. You count factorizations of the identity. That's important. Even for the identity, the opposite element in a sense, you still get a tree-like factor. And that matters. Trees appear a lot in this concept. And you also have the big factorial. All right. So because I'm going to make a point that this is an interesting generalization that we're given, I want to advertise a little bit the fact that these Hurwitz numbers, they appear in a lot of different areas of math. So I'm going to provide evidence by saying that look at all these different methods that people have used to prove them. So originally, Hurwitz and Strel, they used a combinatorial cut and join recursion. Means when you multiply by a transposition, you're either going to merge two circles or break them apart. So this whole cut and join theory, it kind of like originated in these ideas. Strel filled in some gaps that Hurwitz hadn't really written clearly, and there were serious ones, right? And then Goulden and Jackson, also using the cut and join picture, they used generating functionology to prove the formula. So an important ingredient in that proof was Lagrange inversion techniques. Yes, thank you for answering the question in the chat. So the reason that I mentioned these together is they didn't explain the product structure of the formula. Right? So there is, moreover, a very popular geometric proof. It's a much broader setting where we have an ELSV formula. We have a way to connect the counting of factorizations like this and for higher genus. And this turns out to be a geometric object. This goes down to calculating the degree for an algebraic map that is defined over MGN bar, right? The compactification of the space of curves. And this is a difficult object. And this formula comes out of doing certain natural integrations there, but also you cannot explain the product structure. Now, for us, the most important one is this really cute proof that is kind of a little bit unknown, or maybe not, I don't know, in as many people as I would like. So Sheffer, Poulalon, and Tutsi, they did a really, truly immediate bijective proof of that, right? So they did use the usual card theory or map theory, and they translated the factorization to a collection of objects, and it turns out that you had some reasonable labeling structures for the factorial. And the other factors here, there was some sort of trees on the cycles of the permutation. Maybe we could call them relative trees, they call them cacti. I'm just going to say that, if you're not familiar with that proof, check it out. It's really cool. Otherwise, you have to trust me that there is a nice combinatorial argument in SN where part of this formula is explained by using these objects that relate together the cycles of the permutation, as if they were relative trees. Right. So why do they call them Hurwitz numbers? So again, it was because they started with work of Hurwitz, who was interested, however, in enumerating Riemann surfaces. So in fact, Riemann surfaces were that could be branched over the sphere, and you could have prescribed monotomy around the branch points. So this was really interesting because this happened before we had the main kind of like modern day topology by Poincaré. This happened before we had representation theory, and a lot of these new ideas of the 20th century appeared at the time. The definition of the braid group as the fundamental group of the configuration space of points that Sarah was talking about before. A lot of these things or go back at least partially to this really cool work of Hurwitz. Okay, so we're going to be interested in the genus zero case. I'm going to disappoint you if you ask me at the end whether we have a similar picture for reflection groups. I think right now we don't have the technology, but it's a really good question. If you have any ideas about that, we should talk about it. All right. So now I want to kind of like start setting up some material to be able to state the theory. So it's going to be a little bit dense because this project turned out to kind of like blow up. It needed quite a lot of theory builds. In fact, we ended up breaking it into 3 papers. But I think I'm going to give you the basic ingredients. So we're going to change our ambient group. Instead of the symmetric group, we're going to have a veil group. And in fact, our theorem calls for all well-generated complex reflection groups, but I'm barely going to talk about it at the end. It's just it becomes more complicated. So for now, just veil groups. The property definition, before we had that a factorization has to be transitive, as much as the transpositions have to act transitively on the numbers 1 to n. Now, this is a really cool property that does not have an analog for reflection groups. There isn't a natural collection of points or numbers on which a reflection group is acting. So this property is going to be very important for us. We're going to change it, and we're going to say that a factorization is going to be called full if the factors generate the whole group. It's equivalent with being transitive in the symmetric group, and it makes sense in arbitrary reflection groups. And it turns out to be good because it gives us nice structural properties and nice formulas. And we have to thank Gilles Seffer. Gilles was the one who suggested to Joel and Alejandro, who were working on similar problems, whether they could test this property for the identity for all elements, and eventually entered the project as well. Now, we're not going to be able to give a counting formula for arbitrary elements in the groups. We're going to be giving them for parabolic quasi-Coxeter elements. Just keep in mind that these contain all of the elements in the symmetric group. These also contain all of the parabolic Coxeter elements, so it's a big enough family. The definition is that an element is called parabolic quasi-Coxeter if it has a reflection factorization that's kind of tight. that if it is of minimum length, the factors generate a parabolic subgroup. Right? This also has to do, this also has interactions with the root lattice, but let's keep it like that. And let's keep in mind that it's a big enough class of elements. An important object that appears here that generalizes this idea that I was talking about, connecting the cycles of the permutation with a relative tree. This is a relative generating set of reflections. So you start with your permutation sigma, or with your element sigma, and you consider sets of reflections that if you add them to a reduced factorization of sigma, you get a collection that generates the whole group. So they're relative generating sets because they also need a reflection factorization of sigma to become truly generating sets. Now, keep in mind, you can always add a bunch of reflections and generate the whole group, but I'm imposing a condition that has to do with length. I'm saying that I'm allowed to add only n minus the reflection length of the element. So some elements do not have relative generating sets. And it turns out that it is exactly the parabolic Pascal-Oxter elements that do have relative generating sets. All right? Just keep in mind for a bit that there is this nice compatibility because our class of function and this new object that are like relative trees that are relative generating sets. Okay, so now I'm ready to show you our theory. I'm going to use two notations. F full of sigma is the number of shortest length full factorizations, where the factors generate the whole group. And F red of sigma is the number of reduced of shortest length factorizations that don't necessarily generate the whole group. So our theorem is a formula for the full factorizations of sigma that does involve all these objects we talked about. So the relative generating sets and the reduced factorizations. Now, you might be upset with me and tell me, Theo, you're using this other thing that you haven't said anything about, that it might be unknown as well. Well, it turns out that for the parabolic Pascal-Oxter elements, these behave very well. These have very nice product formulas. We still don't understand them too well, but in the parabolic Oxter case, we understand them completely. More generally, we have some conjectures, but these behave well. So you should think of these as part of the product formula. Okay. So I'm going to give you here the correspondence between the main ingredients of the two formulas. You see we have the factorial that appears in both of them. We have these relative generating sets that I'm telling you somehow have to do with the n to the c minus 3 factor. I'm going to explain it in the next slide. And we have a bunch of reduced factorizations that in the symmetric group are really related to these expressions. So in fact, I would like to write it down just so that for the experts, they can see exactly what this is. So we have the lambda i's to the minus 2 here, and lambda i's minus 1 factorial is the length. Now the connection index for the symmetric group for a Young subgroup, just the product of the lambda i's. For the whole group is just going to be n. This is just n plus c minus 2 factorial. And it turns out that the relative generating sets have this nice expression n to the c minus 2 times the product of the lambda i's. So you can easily see that there is a little bit of spreading of the lambda i's around, but the main ingredients are there. Now, I want to point out, somehow, magically, the connection index appears there. So the connection index, it's an important invariant for Veil groups and has to do with the root lattice and the weight lattice, but it also has to do with the Gramian determinant of root vectors. It has something intrinsic to do with collections of reflections that generate the whole group, because these things give you basis for the root lattice and similarly basis for the co-root lattice, and somehow the numerology matches. We don't understand it very well, but it is clear, or hopefully it will become clear, that it's an important ingredient because it appears in the complex case as well. Right. So hopefully I persuaded you that this is truly a generalization of the standard formula. I want to show you this very cool symmetric group argument, which completes the fact that our version of the formula and the standard version of the formula is the same, and there is a reason for that. So if you cancel out everything, the thing that you need to prove is that the relative generating sets for a permutation of psychotype lambda are enumerated by this expression, n to the c minus 2 times the product of the lambda i's. But how many ways can you create relative trees? You have a cycle here and another cycle. And to to create a relative generating set, you have to add some transpositions that make the whole thing a tree, right? So you have to add a tree on the cycles. But for each edge of the tree, you have many options. You can pick whichever of the lambda I numbers here with whichever of the lambda j numbers here. So for each edge, you have lambda I times lambda j options. So if you put them all together, you're summing over the trees on the cycles, and the quantity that you're using is the product of the lambda i's to the degree of that vertex. Now, this immediately becomes by Cayley's theorem, by Cayley's weighted theorem, the expression that we want, right? So the sum of the lambda is just n, and this is the reason for n to the c minus 2. This is a way to count cacti, but I really like this because the same calculation appears in this sort of permutahedra Erhard polynomial structure that recently has become very popular, right? So it's similar things that happen there. So it's kind of like an intrinsic thing. Okay, so a few things about our proof. It has a serious disadvantage, as many of the proofs in this, many of the first proofs of cool theorems for reflection groups have. The disadvantage is that it depends on the classification. So the classification, the Weyl groups and the reflection groups are classified, and we did it case by case. So we calculated both sides of the equation separately, and we compared them, and voila, they're the same. For the combinatorial families, the right-hand side is essentially combinatorial arguments because these families, they're generating sets, they behave like trees. It's similar. And for the left-hand side, we related the full factorizations in these groups with the full factorizations in SM. I have to point out, this is one of those things that is natural when you hear about it. It's pretty tricky. It's quite technically complicated. And when one faces a situation like that, one of the best solutions is to have Joel Lewis in your group, because Joel is really great with these things. So he developed this really nice approach to kind of like characterize the situations that appear and complete the numerology. And for the exceptional groups, we counted again both sides, use computer calculations. For the left side, we used the Frobenius from presentation theory and some Möbius inversion, and the right-hand side is kind of like straightforward. So it's an ugly proof, but a great theory. So, I wanted to point out a few heuristics. So I hope Igor, if he's here, we're not going to hate me because these ones do not work. So it's not as if I'm treating you on anything. I'm just going to point out that there is some compatibility between the combinatorial objects that appear. So here we have something that has to do with reduced factorizations of our element. And here we have something that has to do with completing the necessary reflections to generate the whole group. If you put these objects together, voila, you have a full factorization. So you start with the factorization of your element, and then you pick each of the reflections in the relative set, and you use each of them twice. So then the product, it remains the same. And because you have used all of the reflections in a relative generating set, you have a full factorization. And, it's a good numerology. Here we have Fred many ways to do it. Here we have RGS many ways to do it. And maybe there would be a shuffling or something like that. Well, you know what? It doesn't work. At least it doesn't work in the obvious way that we thought about it. But it's kind of like, it's right there, right? There might be something behind it. In particular, there might be a complicated way to start with factorizations like that, spread them around, change the factors so that they're not really, reduced factorizations here, but do it in a controlled way. The evidence that exists for that is that the whole collection of full factorizations of sigma is in a single Hurwitz orbit. Hurwitz orbit in the sense of the braid group action on tuples of elements. Right? So we hope that this would be an approach that could give us something in the future. Now, I'm sorry, I'm going a little bit faster. There's so many things here that I'm excited about. I think it's a really good project. Some of the side scenes that appeared, or kind of like we hope are important contributions as well, are the following. So I mentioned in my formula these Fred numbers, which is the numbers of reduced factorizations of these things that appeared. And those were kind of like generalizing the lambda i's to the lambda i's that appeared in the symmetric group case. So I mentioned that for all of the classical star elements, these things are always very nice. And this is a sort of discussion of why these are so nice. So for Coxeter elements or parabolic Coxeter elements, this is a known formula that goes back to Lehenga and Arnault and eventually was advertised more by the Cis and Sapoton. It has to do with the number of maximal chains in the non-crossing lattice. It is this interesting chain number h to the n times n factorial of the size of W. H is the Coxeter number of the group. But even if it's not a Coxeter element, I'm giving you here the table of all of the quasi-Coxeter elements in the real reflection groups. All of them, they're products of small primes. Now, this observation, it goes back to Voigt, who was a student of Briscoe, but to me, it was first mentioned by Christian Stum, who did computer experiments and found out that there is a really nice structure here. So I tried a lot to figure out an explanation for that. And at some point, I had this really cool conjecture, but it's been on hold for a while. So it involves this more difficult geometric object that's analogous to the Liasko-Lehenga morphism that appeared in the ELSV formula, also in the Sis's work. And so there is a geometric object that's called the Frobenius manifold that's associated with Coxeter elements, and a degree of amorphism there turns out to be equal to these enumerations. So all of the times for all of the Frobenius manifolds where we know all of this data, it turns out that this sort of conjecture is true. I don't have a good way to explain it, but I feel it is compatible with previous theory. And this also comes with a dual braid theory. So Baumeister and Ries, they developed a way to do presentations for the group just by using the reflection factorizations of quasi-Coxeter elements. So if you're an expert of dual braid things, this would sound natural to you, but it's interesting, right? So these give presentations of the Coxeter group, not of the braid group, but they do give presentations of something else, possibly the complement of some other discriminant. So cool stuff for the quasi-Coxeter elements. Now for the complex, do I have another 4 minutes? Is that it?
Yeah, 3 minutes.
So for the complex reflection groups, just briefly, this is the real theorem, right? The real theorem holds in high generality. For all complex reflection groups that are well generated anyway, we can give a formula for the full factorizations of quasi-Coxeter elements. It doesn't look as good because this first formula has a product structure in a sense, even if this object is a little bit weird. The true formula has this object becoming a summation. So instead of just adding, the index of one group over another, for each element, for each relative generating set, we calculate the quotient of two Gramian determinants. Now, for expert, it's clear that the connection index can be realized as a Gramian determinant with associated roots. But in complex reflection groups, these Gramian determinants are complex numbers. They're not integers. And somehow magically, when you add them together, they become integers and they count something. This is remarkable. And it's even more remarkable because it's not an accident. These things have appeared before. So Breker and Michel, they managed to define good analogs of root systems for complex reflection groups. And in those analogs, exactly these Gramian determinants play the role of the connection index. It wasn't a complex number, but it was the idea that was generated by this Gramian determinant in an extension of the rationals, but it was meaningful. And so the same kind of like numerical quantity magically counts factorizations here. So I feel there's something that truly involves the behavior in a lattice and the core lattice, but we still don't understand. So I'll say one final thing. A reasonable question is, what can we say about the higher genus case? The LSV formula in particular tells us something about arbitrary genus factorizations. So we don't have formulas, but we have observed a really good structure for the generating functions. So here we have the generating function where we take arbitrary length full factorizations of a fixed permutation. So, the generating function is with respect to the number of factors. We're not changing the group at all. This is an important distinction to previous work. And it turns out that these sort of generating functions, they always have nice formulas, nice expressions. They're always a finite sum of exponentials. And it turns out that you can predict a few things about them. There is a factor that involves the length of an element. There is a factor that involves the number of hyperplanes, and there is a polynomial that looks really cool. So this is part of the modeling, let's say, of the expression of the generating function, and it's characterized by this polynomial. And these polynomials are often unimodal. They always have integer coefficients, but sometimes the coefficients can be negative. So this is the cyclic group of order 6. So as we're talking about these things, Alejandro had this amazing idea to just plot the roots of these polynomials. And these things look amazing. It's just ridiculous. So they're very rigid. These are in the appendix of our paper. It's going to show you those that look a little bit nicer. So look at that. These are roots of a polynomial of polynomials that encode the number of full factorizations of elements in these groups, of the identity in each of these groups. Look at the structure of these things. It's remarkable.
So,
Anyway,
Theo,
yes.
your time is up, so you should bring it to close soon.
This is it. This is the final thing that I wanted to say. So I had another thing about the homogeneous case, but I just wanted to point out the nice product structure of these generating functions. Anyway, so we have broken it into 3 parts. The first one is on the archive, and the other ones are coming soon. Thank you very much. Have a happy 20.
Thanks so much for a lovely talk. And are there any questions? Actually, there was a question in the chat. It says, what are the advantages of using Sage for your calculations as opposed to, for instance, Maple or Magma?
I mean, a big part of it is just that we're more comfortable with Sage. Sage also connects different programming environments. In particular, Sage plays very well with GAP, and GAP has a good structural presentation for complex reflection groups as permutation groups. So through Sage and GAP, and the work of Jean-Michel and Sevi and other people, you can do very easy character calculations, which is what we needed to do for one part of the project. Also, Sage is open source.
Open source, yeah. It seems to become the standard for doing combinatorics, at least. Are there other questions?
I have a quick question. Do you suspect any relation to integrable hierarchies, partial differential equations, anything along those lines?
So that's a good question. This is one of those things that does in fact appear. I couldn't put it in. The idea of the cut and join equation is fundamental, right? And it's natural. It just says you have an element, you multiply with transposition, what happens to it? You can ask the same thing here. You have an element, you multiply with a reflection, what happens to it? It turns out you can get the recursion in a good way, like the things that will appear if you test this formula are going to be smaller parabolics or elements of higher length. So you can do the recursion part, but to do the hierarchy or to even do the differential equation, that's a little bit tricky because one advantage that is hidden in the Gould traction approach is that you have a variable for its cycle length, essentially. Well, in this situation, you can have quasi-Coxeter elements or Coxeter elements that have the same length but are of different type. So you would have to have like a fake variable for each type of those, and it's unlikely that something would behave very well, at least not easily. So I'm not sure.
Other questions? Okay, well, let's thank Theo again for a lovely talk. And this